Well, I'd like to welcome everybody to this session, which is why does damage to scientific progress, what does damage to scientific progress look like? And this will provide examples of critical analysis. And I'd just like to reiterate that all scientists should ask lots of questions and look at their and other science critically. My name is David Vaux. I'm on the board of the Centre for Scientific Integrity in New York, which is sort of like the board governing the Retraction Watch blog. And I'm very much looking forward to this session. We've got three speakers that are each going to speak for 15 minutes. There's Kirsten Parris, who will be speaking first. Then there'll be Timothy Clark, the second speaker, and the third speaker in the session is Gideon Meyerowitz-Katz. So without any further ado, I'll hand over to Kirsten Parris, who's an ecologist in the School of Ecosystem and Forest Sciences at the University of Melbourne, where she conducts research on communication by birds and frogs in urban landscapes. And she'll talk about the practice of toe clipping in frogs in field studies. So over to you, Kirsten.
Thanks very much, David, and good morning, everybody. All right, set to go with the slides, David?
Yep. All good.
Thank you. So today I'm going to be talking about the toe clipping wars revisited. And this is a topic that some of you are very familiar with, but others maybe less so. So I will give a bit of background and introduction. Mark recapture studies are done in field ecology and zoology to estimate population sizes of wild animals. In essence, an animal is caught, marked in some way and released, and then recaptured at a later date. And a key assumption of mark recapture studies is that there are no effects of marking on the animals. The return rate, that is the probability that you will see your animal again, is a function of survival rate, that is the animal still alive, and the probability of recapturing it if it is alive. So any reduction in return rate could be due to reduced survival, reduced recapture rate due to changes in behaviour of the animals, or both. So it's really important to consider the impacts of mark recapture studies if the marking method is having an effect on our study animals. First of all, because it produces biased data, and second, because we may be harming our study animals inadvertently. So toe clipping of frogs is a very common method of marking frogs that was introduced in the 1950s. And in essence, toes are clipped off frogs in a variety of different combinations, and then that enables us to identify individuals when we catch them again in the future. Back in 1972, which is now almost 50 years ago, Clark found a negative effect of the number of toes clipped in Bufo fowleri, Fowler's toad, on the proportion of the animals that were recaptured. Here, the data are divided into two groups for the larger animals and the smaller animals, but each of them showed a very similar decline in recapture rate with number of toes that increased. However, other studies that were published later apparently showed no effect of toe clipping. So my co-author and I, Michael McCarthy and I, investigated this further by reanalyzing published data sets on toe clipping. And it turned out that the apparently inconsistent results were due to the inconsistent statistical power. Where power was adequate, we always found a negative effect of toe clipping on return rates. After some interesting experiences with the scientific publishing, forgotten my noun, this is what happens in COVID times. Anyway, an interesting experience through a variety of journals. This paper was eventually published in Amphibia Reptilia in 2001, so about 2 years after we first submitted the first version. And we included data on a third species of frog. And while I don't have time to go into all the responses we received to our study, it's always enlightening to consider the comments of Dr. X, who was one of our reviewers on the first version of the paper. And this encapsulates the resistance to the idea that toe clipping can harm frogs and that we should change our practices. Dr. X had clipped thousands of toes off thousands of frogs, had never seen an effect. She implied that we were bringing our own personal concerns into this situation, that we weren't only data-based. But it's interesting to say that we were using maths to make inferences, which indeed is what we were doing, but we thought that that was actually part of scientific practice. She equated our activity with animal rights activism and also considered that we were bringing our personal feelings into the work. So moving forward a few years, Mick McCarthy and I published a second paper which included a Bayesian analysis of these same data. And this was a little more elegant, and it allowed us to consider what would happen if the change in return rate actually varied depending on the number of toes that had already been clipped from our animals. And so here we see the change in return rate relative to 1 toe removed for 2, 3, 4, etc., down to 8. And we can see that the effect of removing a second toe is relatively small, but once we're removing, say, 4, 5, 6 plus, the probability of seeing our animal again is really substantially reduced. And this is just a regression model showing that same relationship, relative return rate on the y-axis as a function of number of toes clipped. And the predicted relationship is in the unbroken line, and then the dashed lines show the credible intervals, 95% credible intervals around that relationship. So this second paper was published in Journal of Applied Ecology, which is clearly more widely read than Amphibia Reptilia, and it led to all sorts of outrage and responses in the literature and outside the literature, including some rather personal attacks on me and Mick. There were, in summary, a lot of unhappy people who didn't want to receive the message that we appeared to be sending in our work. And a variety of people pursued additional studies, and it seemed mostly in an attempt to prove that we were wrong. However, there was a lot of diversion and confusion, and people were undertaking studies that weren't actually going to answer the question or present data that showed that when we were capturing, marking and releasing wild animals, that toe clipping was not having a negative effect. For example, people might have done a study of animals in captivity, and if an animal is housed and it's protected from predators and it's fed regularly, then the effects of having its toes removed could be quite different to what that animal would experience in the wild when it had to fend for itself. There was a lot of bold claims made about the value of information that we gain from mark recapture studies, basically saying we have to do these types of studies to gain the information we need to conserve frogs. And frogs are a group of animals that are declining all around the world. And if we don't do these studies, we can't conserve them and they will go extinct. And there were also some quite alarming further misunderstandings of statistical power and inference in a range of published studies. And unfortunately, I don't have time to go through all these examples today, but I will show just a couple of them. So in 2008, Waddell and colleagues investigated the return rate of frogs as a function of toes clipped in 2 species. This one is the green tree frog, Hylas cinerea from North America. And here we can see the estimates of return rate and their confidence intervals. And these overlap very strongly with our existing relationship. And Waddell and colleagues stated that, yes, indeed, in the green tree frog, they're following the same pattern of McCarthy and Parris. But for this species, the squirrel tree frog, they instead said that these frogs were behaving differently and that toe clipping did not have a negative effect on the return rate of the frogs. And this is because their estimates for return rate for frogs that had 3 or 4 toes clipped removed were very similar. But if you look at the confidence intervals around those estimates, we can see quite a deal of uncertainty and also a very strong overlap with the previous relationship. This was a study that was published in 2014 with a very definite title, "Toe clipping does not affect the survival of leopard frogs." So this study was conducted in the laboratory, so not on wild animals that were released to fend for themselves post-toe clipping. A couple of other notable things: the entire study included 100 individuals, and in our first paper, the one published in Amphibia Reptilia, we indicated that to find an effect on wild frogs, we would need a sample size of probably around 400 individuals. So the sample size was low to start with. They also clipped up to 12 toes off the frogs, just to be sure that they would really see an effect. And frogs only have 18 toes to begin with because they only have 4 on their front feet. So 12 out of 18 is an astonishing number of toes to clip. These were the results. The percent survival of frogs on the y-axis as a function of number of toes clipped. And indeed, we can't really see very much of a relationship here. But let's have a look over here at the frogs that had no toes clipped. Only 40% of the animals survived over a 13-week period in captivity. So that is an astonishingly low rate of survival for captive frogs. I've had pet frogs that live for years and years, only lasting for 3 months is a bit strange. And then it turned out that actually the entire population of frogs was infected by a bacterial disease, which was killing off the frogs that had no toes removed as well as the other ones. The authors argued that this demonstrated even more strongly that toe clipping didn't have an effect, because you'd think that with that disease around, the toe clip frogs would be doing even worse, and they weren't. Anyway, moving on. Here's another bold title: "Toe clipping does not affect the locomotor performance of frogs." And in this case, the study was done on the natterjack toad, Bufo, or now known as Epidalia calamita from Europe. And this frog's looking a bit grumpy, and you can probably see why. Unimpressed with their interpretation of their results. So let's have a look here at this graph, which shows the sprint speed of the toads, how fast they can run on a treadmill, broken into 2 groups, whether they've had their toes clipped or not. And we had about 60 animals in each group. Here are the estimates, and here are the standard error bars. So not 95% confidence intervals, but standard errors. And we can see here that the authors did not find a statistically significant effect of toe clipping on sprint speed. But they also say that they calculated the power, and the power of this study was incredibly low. And in fact, to detect an effect, they would need about 61,000 toads instead of 120. Yet they still state that there was no effect of toe clipping on the sprint speed of their animals. So that's the bad news, but let's think about the good news. And there has been substantial progress in this debate in the last 20 years or so, as one would hope to see. So many animal ethics committees are now discouraging the use of toe clipping, particularly when researchers are studying endangered species or those that have very low population sizes. There's now, if you look in the literature, substantial interest in alternative marking methods that could replace toe clipping and still do the same job of marking our animals in a way that is consistent and efficacious, but with potentially less impact on the study animals. Pattern mapping, also known as photographic mark recapture, has shown to be effective for a range of species. And this is a method in which an animal is caught and its photograph is taken, and individual patterning on its belly, its ventral surface, or its back, its dorsal surface, can be used to identify that animal again if it's captured in the future. And I did a sweep of the herpetological societies across the world to look at which ones are using, are considering toe clipping, and a couple of them have codes of conduct that consider this. So very quickly, I'd like to acknowledge Michael McCarthy, my co-author, Fiona Fiddler for her continuing interest in this work, and all frogs because they're amazing, and I hope to do my best to conserve them in the future too. So thank you.
Thank you very much, Kirsten. We will hold off questions that I'm taking note of in the chat forum after the three speakers have finished their presentations, and then we'll get them to answer questions together. And so now we'll move on to the second speaker, who's Timothy Clark. He is an ecologist at Deakin University, and he has encountered unexpected levels of questionable research practices. And he will talk about the importance of research integrity and transparency in combating the reproducibility crisis. So take it away, Timothy.
Thank you. Thanks for the invitation today. First up, I'd just like to thank a couple of my collaborators, Dominique Roche and Sandra Binning, because this talk is an adaptation of some things that they've spoken about previously. So as we all know, science begins with questions, and then we conduct the experiments to answer those questions. We get our results, and then hopefully we publish the results. And this is a really key point, because if we don't publish the results, then it's kind of like the research was never done in the first place because nobody finds out about it. So publications are essentially the currency of scientific success. And the more you publish and the higher impact journals you publish in, that's better for your CV. But it's been proposed that this push to publish lots of papers in high impact journals has led to the natural selection for bad science. So this selection for higher output leads to poorer methods and increased high false discovery rates. And indeed, that is what we see. So many scientific disciplines face what we know is termed the reproducibility or the replication crisis, where a large proportion of results can't be independently validated by other labs. This has been shown in fields such as psychology and biomedical science, where about 2/3 of published findings are estimated to be incorrect. So as an example, in psychological science, this collaboration, the open science collaboration, attempted a mass reproducibility program. There were 270 authors. They attempted to replicate 100 studies in 3 psychology journals, and they only managed to replicate 39% of the effects in those original studies. So we've got more than 60% of the effects that had been published could not be replicated by independent parties. It's a similar story in oncology, where there was a large reproducibility effort where 53 landmark studies in cancer research were attempted to be reproduced, and only 6 of the studies, or 11%, were successfully replicated. And this is becoming increasingly more recognized. There's kind of a loud minority of people who are pushing for change in this area. And obviously the forum that we're at today is a part of that push. Irreproducible results in biology might not be as damaging to humans and to human welfare as those in medicine and psychology. However, they can have devastating effects on public perception of scientists by promoting mistrust and denial on a range of topics, including evolution, climate change, pollution, overfishing, etc. So what explains replication failure? There can be honest error, various biases, conscious or unconscious biases, which we've heard about in the previous talk. Small sample sizes is a common one, which we also heard about in the previous talk. Selective reporting of data, p-hacking and other questionable analytical practices, unreliable methods, and there can also be outright misconduct or fraud. And this is something that scientists generally don't like to talk about. Everybody gets a little bit funny when you start talking about fraud. We like to assume that it doesn't exist, but there is plenty of evidence to indicate that there is quite a bit of it going on. It might not be anywhere near the magnitude of the questionable research practices, but there's certainly enough to be causing a substantial amount of damage. So what is a replication? There's lots of terms and definitions. I'm not going to go through all of these, but I've just bolded a couple here: direct replication and conceptual replication. And one thing to note here is that there is no such thing as an exact replication. Every single replication attempt is going to differ in at least some very small way from the original study. That's unavoidable. But a direct replication is a study that attempts to recreate the critical elements of an original study. So set the same samples, procedures, measurements taken, etc. It must duplicate those elements that are believed necessary for producing the original effect. Whereas a conceptual replication tests an extension of the theory to a new context. For example, whether an effect extends to a different population, a different life stage, a different species. So it essentially tests the generalizability of an effect. A conceptual replication does. So that brings me to some of our research on fish. I'm a physiologist is my background, but we got interested in some of this research on fish behaviour and sensory systems. So we're talking about with reference to ocean acidification here. So elevated CO2 levels in the oceans is driving down pH and causing what's known as ocean acidification. There's been decades and decades of literature previously by a lot of fish physiologists actually looking at the impacts of really elevated CO2 on on physiology, survival, growth, etc. And there were never any alarming consequences. It seemed that fish were pretty well adapted to accommodate higher CO2 levels because they have pretty sophisticated acid-base regulation systems. But then about a decade ago, some literature started to emerge that relatively low CO2 levels compared with what had been used previously in studies was causing really severe behavioural and sensory disturbances. So these were CO2 levels that are projected for the end of this century, so in the 800 to 1,000 microatmosphere range. And it seemed that coral reef fish were the most sensitive. And these impairments ranged from impaired vision, impaired hearing, impaired or altered olfaction, attraction to predators or to the chemical cues of predators, impaired brain function, increased activity, increased boldness, risk-taking. Essentially everything that was looked at in these coral reef fish was apparently pretty severely altered by these end-of-century levels of CO2. And here's just a handful of the papers that were coming out, and note that they're very high impact journals as well, so it garnered a lot of attention. Here's just an example. So this is a metric for activity levels, mean number of lines crossed in an aquarium. And you can see as the CO2 level increases up towards the levels that we expect by the end of this century, you see a 9,000% increase in activity levels. So that this is the kind of results that we were talking about. Many species were reported to be affected. So here we've compiled a bunch of data from various different studies through time. So time is increasing as we go down the page, and these are all different species as well. And you can see a pretty consistent theme here. So these are choice flume studies. And here's a diagram of a choice flume down the bottom here. Essentially a fish goes in and it gets to select which side it wants to sit on. The side that has water flowing through that's just clean seawater, or the water that's flowing through that is seawater plus chemical cue from a predator, for example. And back to the graph over here. So this is the time in the predator cue stream. And you can see that the fish that are under high CO2 levels spend almost all of their time on the side of the flume that contains the predator chemical cue, whereas the control fish under ambient CO2 levels essentially spend 0% of their time on that side of the flume. So we're not just talking about an impairment in their sensory abilities, we're talking about a complete reversal. So the high CO2 fish had almost complete attraction to the predator chemical cues compared with the normal response, which is to avoid those cues. So this is absolutely remarkable findings, and that's what drew my attention to it in the first place. And just I wanted to note the incredibly small variability around a lot of these as well. So it's pretty much every single individual is behaving like that. There's very, very little variability between individuals within treatment groups. So the first step was to request a transparent collaboration where I could get to go and see these experiments taking place, and we could start building on them, because I was interested in understanding the physiological mechanisms behind a lot of these weird behavioral alterations. But I was told that that won't be possible because there's certain people that do the behavioral tests, and they do those behind closed doors, and it wouldn't be possible for me to be involved in those. And that didn't really satisfy me. So the next step was to try and replicate the work ourselves. So it didn't exactly go according to plan. And if anybody's interested in the background to a lot of this, there's a blog on the Ecology and Evolution website there that you can go and have a look at. But I'll I'll talk through some of the results of that study now. So we conducted it across 3 years. We kept on coming up with different ideas that could potentially be used to downplay our results. So we went back the following year to either the field site or we conducted more experiments in the lab. We used over 900 fish individuals across 6 species and different life stages, from larval fish all the way up to adults. We tested a few different behaviours, avoidance of these predator chemical cues using the choice flumes that I mentioned before, activity levels, and behavioural lateralization, which is really just it's looking at preference for turning left or right, which has been reported to be altered under high CO2 as well. And we ended up getting these results published. Today, and an important point as well is that 4 of our species had been used before and reported to be severely disturbed by the elevated CO2 levels projected for the end of this century. I'm just going to concentrate on probably the most profound results that had been reported, and that's this predator cue alteration to predator cue chemical cue avoidance. So this plot on the right-hand side here is what I've shown you previously. So this is from Dixon et al. In 2010, just showing that fish under CO2 spend 100% of their time in the side of the flume containing the predator chemical cue, whereas control fish don't spend any of their time in that side of the flume. They spend all of their time in the side of the flume containing no predator cue. We didn't want to present bar graphs, so all of our results are presented in time series, but just to show you what this would have to look like in a time series, you put the fish into the flumes down here. So this is assumed to be the control over here and the high CO2 here. The control fish would immediately have to go to the side of the flume that doesn't not contain the predator chemical cue, whereas the high CO2 fish would have to go to the side of the flume that has the predator chemical cue going down it. So that's what it would look like in a time series. The high CO2 fish goes into the predator chemical cue, the control fish goes away from it. At the halfway mark, you turn some taps and you modify the side of the flume that is receiving the predator chemical cue. So at that point, the control fish finds itself in the predator chemical cue, so it would have to immediately sense that and move back and move around to the other side, and vice versa for the high CO2 fish. So you would end up with this kind of plot where the high CO2 fish moves to the other side and continues to maintain itself in the predator chemical cue. If we go to our results now, so here's our time series. We have a time in predator cue. So in the gray would be somewhat attracted to the predator chemical cue because they'd be spending more than 50% of their time on that side of the flume. In gray dots, we have the control fish, and in blue dots, we have the elevated CO2 fish. You can see there's no difference between the two. Both of the treatment groups are avoiding the side of the flume containing the predator chemical cue. Another species, we find the same thing. Another species, same thing again. And then this species was the only one where we detected that the elevated CO2 fish seemed to be a little bit impartial to which side of the flume they were on. They were just kind of hanging around the 50% mark. So we repeated experiments on this species the following year with a lot more individuals and across more life stages. And here are those data for the subsequent year where we have one of the same species repeated, or a couple of the same species repeated and an additional species as well. We did a lot longer experiments here because we thought that maybe they just needed a lot more time to settle in the choice flumes. So we gave them 40 minutes with just clean seawater going down both sides before we dialed some taps that allowed the chemical cue to start flowing in. You can see that there's no difference, again, between the control and high CO2 groups for any of these species. You also note that some species just responded much more cleanly than others, despite this being the exact same setup, and we were actually using species one after the other. So there's some interesting species effects here where this species just seems to be a little impartial to the setup that we were using and the predator cue that we were sending down compared with these species over here. But the end result, no difference between control and the high CO2 fish. Now I'm just going to briefly talk about this bootstrapping data simulation
Time is
technique.
fleeting, so you'll have to be quick.
Yep, okay. So that's just reiterating that we see complete attraction under high CO2 and complete avoidance under control conditions. And this is consistent across studies with very minimal variation. This is a plot here of the variance that we would expect to see in these results based on our huge data set of these actual experiments. And then the dots here represent the variance that is in the treatment groups in a lot of the previous studies. You can see that the variance in those previous studies is well below what would be reasonably expected, given the different sample sizes that you might have in your study. So our study had both direct and conceptual replications. We used the same species, same life stages, and we also tested new species. We had improved methodology where we videoed everything. We had automated tracking of the fish on those videos, so none of it was subjectively evaluated by us. The climate change deniers were thrilled, unfortunately, but the important thing to note is that the problem is the exaggerated unreplicable papers, not the transparent attempts to replicate those findings. And you can read more about that in this article by investigative journalist Martin Enserink in Science. And notably, there was a previous case that colleagues and I were involved in where misconduct was alleged and essentially found there was mass data fabrication, and this paper ended up being retracted. So how can we improve transparency and reproducibility? We can have open data and code, pre-register papers as well. And also I think for very subjective kind of behavioral studies especially, we can have visual evidence of what we're seeing. And I make the case for this in a previous article there. With that, I'd like to thank my colleagues and thank you for the invitation once again. Thank you.
That was absolutely fantastic, Tim. And I know that your paper and the retractions have been covered in by Retraction Watch, and also the ones that are going to be from our following speaker, Gideon Meyerowitz-Katz. And we'll perhaps discuss a little bit about that after he's given his talk. So Gideon Meyerowitz-Katz is an epidemiologist at the University of Wollongong. He writes a regular health blog covering science communication and public health, and he will discuss how meta-analyses failed, the tale of ivermectin and COVID-19. So I'll pass over to you, Gideon.
Hi all, yeah, I hope you can see my slides there. I'm just going to bring up the timer for myself. Brilliant. So, hi, I'm Gideon Meyerowitz-Katz. I'm an epidemiologist at the University of Wollongong. I also I work for the state government as well, and that has required a lot of COVID stuff, but my main job before COVID came is in chronic disease. And more recently, I've somehow managed to get involved in ivermectin for COVID-19. So what is ivermectin? Sorry, I'm just going to go through very briefly the beginning, some of the main events that happened during ivermectin and kind of where we are sitting now. And I think just quickly, it's important to note when I say meta-analyses have failed, and I titled that somewhat provocatively, I know, but it's not because of any specific person who did something wrong. in terms of meta-analysis, it's more that the current methodology that we use for meta-analysis is not geared to detect people who are being dishonest. And that is pretty much the central thesis of this talk, and also what we've proposed in some published literature now. So the beginning of ivermectin. Ivermectin is an extremely safe medication. It is given each year to hundreds of millions of people worldwide, perhaps one of the most used medications of humanity, genuinely. The World Health Organization gives ivermectin as a treatment for parasitic diseases in mass drug administrations where they try to get to every person in a country. And it is amazingly effective at treating things like river blindness, scabies, and other parasitic infections. It really is, to some extent, a wonder drug because it has largely eliminated some of these diseases from the world. At the very start of 2020, initial in vitro research showed amazing promise. So this study by Haley et al. From Monash University was published on April the 3rd, 2020, and finding that in cells in petri dishes there was, or in SARS-CoV-2 rather, so RNA more, in petri dishes there was a huge reduction in viral replication. That paper is now among the top probably 1,000 or 5,000 papers ever published in terms of citations. I checked on November the 9th. The first time I checked how many times it had been cited, and it was 1,634. Now it is up to about 1,700. So in the course of a month, 50, 60 citations. After Haley et al., very shortly after, this preprint was published online by Surgisphere. So now most people know the story of Surgisphere. I'll briefly recap. It was a group, an American company that claimed to have a very large database of patients across the world, where they were looking at various medications that these people had taken and whether they survived COVID. The main two papers that most people know about were the papers published in the New England Journal of Medicine and the Lancet. Those received a lot of attention, particularly in the media. What received slightly less attention was that they published a preprint on SSRN, which was more impactful, arguably, but not so much in the developed world for whatever reason. In Latin America, particularly, and in some other countries in the Middle East and Asia, this preprint had a very dramatic impact. It claimed a 70% survival benefit for ivermectin in this huge database, and it caused governments to change their policies to recommend ivermectin as a COVID treatment almost immediately. It was later withdrawn because Surgisphere probably never had any database at all. While there's some, opacity to the story, they've never come up with the database, and the lead author, I think, has never actually produced any data suggesting that he had this database to begin with. Almost certainly fraudulent. However, because of Surgisphere and because of this initial promise, there was a huge research interest in ivermectin. Now, this doesn't quite match up to hydroxychloroquine, for which there are over 300 studies registered on clinicaltrials.gov, but it is still one of the most researched COVID medications in terms of the number of studies. And in between when Surgisphere was registered, the preprint was registered, and when it was taken down, there were nearly 40 studies registered. So there was a huge interest sparked by Surgisphere, and also it gave legitimacy to the idea that ivermectin worked. And towards the end of 2020, the initial results from these registered studies started trickling in, and the benefits were enormous, genuinely enormous. So this is one of the studies that came out towards it was initially pre-printed towards the end of 2020, and it was published in May 2021. This is a graph from their study where they found that the CT value, which is the number of cycles it takes to detect a result in a PCR test, was far higher in ivermectin than the control. Basically, their interpretation and some people's interpretation is that this indicates almost complete clinical cure for ivermectin with 3 days of treatment versus a control group, none of whom were cured. And the Cohen's d here is 3.5. So this is regardless of your perspective, this is a vast effect size. And so that led to some initial reviews. And this is a non-systematic review by a group led by Pierre Corey. It was published in, this was January or February 2021. And as you can see from the figure description, the benefit for ivermectin was truly enormous, just huge. So that you aggregate all these studies together and you find that there's, this found a 72% or 71% reduction in deaths if you give ivermectin to people compared to control group from both observational and randomized trials. Although I will note it's quite funny that they've misclassified several trials here. Well, it's not quite funny, it's quite worrying rather. They've misclassified several trials here. Some of those they say are RCTs are certainly not. Also, a worthwhile thing to note is these two trials, because I'm going to be speaking about them soon. These are two of the most positive trials on any drug that I've ever seen. I had to, the last treatment that we found where there were randomized trials that found benefits like this, or that I could find, was antiretrovirals for HIV, where you find a 90% mortality benefit after a short course of treatment for a medication. And those were obviously of not just one drug, several drugs, numerous antivirals for people who were dying of AIDS. So these two studies, I'll just go through very briefly. The first one was published eventually in May 2020, pre-printed in published May 21, pre-printed May 2020, November 2020 rather, and by this group in Iran, and the second one by this group in Egypt, pre-printed. The first preprint posting date was also end November 2020. And they respectively found 70 and 90% benefits in a randomized clinical trial for ivermectin on mortality. And this led to systematic reviews like this. This is, I think I can say quite reasonably that this is the most read systematic review ever published in the history of meta-analysis. So it was published, it has an altmetric score of, I think about 40,000. It's one of the most viewed studies ever. And their findings were enormously positive. They found that moderate certainty evidence finds that large reduction in COVID deaths are possible using ivermectin. Also contained this interesting statement, which was clarified publicly by the authors as indicating that any trial they had included in their study should be considered as peer-reviewed because that's what they did in their study. They reviewed them. It's worth noting that if I bring up their table of kind of the risk of bias, you've got these two trials again, NIAI and El-Ghazar. Risk of bias rating is always subjective, of course, and there's no perfect way to rate a clinical trial for its risk of bias, but it is rather interesting. The two trials that I'm going to speak about just now were rated as generally quite good, whereas if you look very close, I know it's hard to see, Lopez Medina, which was actually quite a rather excellent clinical trial, where they made one major error in randomization, but they kind of did sensitivity analysis and presented all of their data and have publicly shared their data, was rated as very low risk and didn't find any benefit from ivermectin. Was rated as high risk, terrible study, and excoriated in this review. So El-Ghazar, I'm going to briefly skip over this. You can read the Guardian investigation if you want all of the details, or my own blogs, or some of the other blogs out there about it. A medical student named Jack Lawrence noticed some very serious plagiarism throughout the text, and decided he was actually assigned it in his master's degree, and he noticed some very big issues. In one remarkable case, they had changed the name of SARS-CoV-2, which is severe acute respiratory syndrome. They'd put it through a synonym finder, and they'd made that into intense acute respiratory syndrome, which led him to check the entire thing, and basically the whole thing's plagiarized. Almost certainly never happened, the study. The data file that authors posted publicly online is fake, with patients who died before the study started, among numerous other issues, copy-pasted patients, all sorts of things. And if you take this meta-analysis that I talked about, the Bryant et al. Meta-analysis, which, as I said, is probably the most read systematic review of meta-analysis ever published. You replicate it. This is an exact replication of their meta-analytic model. I used Starter, but they used RevMan. The Dersimonian-led model is precisely identical in both. If you exclude El-Ghazar et al., you'll see that the point estimate moves much closer to the line of no effect and is, it's just about significant. You get a p-value of 0.05 here once you've excluded El-Ghazar. But the entire effect rests on this one study, NIAI et al., which I pointed out earlier. Now, NIAI et al. Has not been retracted. The journal says that they are investigating 6 months after we've raised concerns. But we have looked into the study, and the first issue is that it cannot possibly have been randomized. This is actually identifiable from the summary statistics they present in their table of results directly. They've changed, they don't have the correct p-values in their summary statistics, so it looks like it's all fine, but if you actually rerun the chi-squareds and the t-tests, you'll find that the groups are enormously different at baseline. And if you look at the actual data itself, the differences are billions to one, or hundreds of billions to one chance that they actually randomize their participants. More worryingly, the data file that we've been sent by the authors contains inconsistencies not consistent with an actually done clinical study. So it may not have occurred at all. The journal says that they're investigating, but hasn't responded to our emails in several months. The problem is that the entire effect rests now, once you remove the fake study, on another study that may also be fake and is almost certainly not randomized and should be excluded. I'm not going to go through everything. We can talk about this in the discussion, I guess, and the questions. There are so many examples of this. We currently have 18 studies total where we have very serious concerns about whether the studies were conducted. I mean, there's one study claiming to be randomized where the authors had a randomized clinical trial set up on March 15th, which was 2 weeks before the findings of the initial preclinical data came out, and was before the just after the World Health Organization declared COVID pandemic. It's one very brief example. Where we are now, if you repeat the analysis, you exclude those two trials, Elgazani and one other trial that claims to be randomized, but say they randomized people by allocating them depending on which day of the week they came into the hospital. You get this result. Oh, and if you include three new studies that have come out since Bryant et al. Was published. Cochrane said this about the ivermectin literature, and just so I don't go over time, I thought I'd note very quickly Andrew Hill's team, who I think you can reasonably say are the most have displayed the most integrity of any scientific group that I've ever come across. They had a study where they had a published meta-analysis where they said ivermectin is extremely beneficial, or that was their main finding, and they said this is low certainty due to the low quality of the evidence, but we think this is reasonably true. They retracted that immediately on discovering the fraud. They've now rerun their meta-analysis, and this is basically the result. If you take all of the studies, including the fraud, you find that there's a massive benefit. If you exclude the fraud, you find that there's a kind of verging on massive benefit. And if you exclude studies where there's very high risk of fraud or very high risk of serious issues in the trial, you find that there's absolutely no indication of benefit at all. The confidence interval is just huge. And there's a lot of potential for publication bias as well. So that is the end. Wonderful.
All right, so now we'll have some questions, and then after that we'll go into some breakout groups. I guess all of these three examples were looking at science in general, which is usually based on trust of other scientists. But there are some cases where you have reasons to question or distrust the honesty of other scientists, and the issue then arises is, what do you do about it? Are you able to reproduce the study yourself? Who do you raise these questions with? Do you write to the authors? Do you write to the journals? Do you write to institutions? And just to get on my own personal sandbox, I'd like to say that in Australia, in many countries, you can write to a National Office for Research Integrity. So 23 European countries, the US, China, Japan, Canada, UK have various national bodies that handle issues related to research misconduct and managing concerns of research misconduct. But Australia is one of the only countries in the world that doesn't have a National Office for Research Integrity. And in Australia, we have the self-regulation model in which institutions are responsible for handling allegations of misbehaviour by their own personnel. And I think this is a recipe for conflicts of interest. Now, I'll be looking at the chat screens, and if you have any questions, please raise your hand and unmute yourself, and then we can listen to your questions, and the panel members will try to address them. So panel members, you can turn off your muting, and we'll see who raises the first question. I'll take Chairman's privilege and ask each of you whether you've suffered any kickback from your efforts to try to raise doubts about publications. So I'll start with you, Gideon, seeing I can see you there on the screen.
Yes, yeah, absolutely. I currently, the authors of the Brian et al. Meta-analysis are part of the British ivermectin response development group, several of them. They call themselves the Bird Group. The Bird Group currently has lies about me up on their website. They are accusing me of fabricating data, and it's remarkable because it's very easily verifiably untrue, because you can just click a link and get all my data. I've got a number of people, I mean, constant attacks on Twitter, several death threats due to ivermectin, anonymous people emailing me, you know, range of stuff. Ivermectin has somehow has gotten people more passionate than anything I've seen before, even vaccines, which is quite remarkable.
Yeah, yeah. What about you, Timothy? Have you suffered any backlash from your efforts to try to alert people to problems in the literature?
Yes, certainly. I would say that the majority of feedback has been positive, but I think that the negativity is often kept quiet behind your back. But yeah, Twitter is a great forum for people to get anger off their chest. So we've been told that the driving force for our study was cruelty, and that we've been called disgusting, and that Nature published a clickbait paper. So there's certainly a bit of resistance there. And just to follow up on a comment that was made before, the institutions seem to do a pretty good job of sweeping things under the rug, some worse than others.
Yeah, indeed. Kirsten, have you suffered any blowback from your efforts?
I have, but largely it occurred in the pre-Twitter era, so it's probably something to be thankful for. And also, while toe clipping of frogs is big news in certain circles, it's not as big as ivermectin for COVID, or you know, we weren't on the front page of Nature disproving you know, really high-profile studies about fish and ocean acidification. But certainly, and you probably could see that in some of the comments that I posted from Dr. X, all along since the very beginning, there has been an attack on us personally. A suggestion that what we're doing is not motivated by science, that and I've heard these comments from, you know, other people who've picked them up about, you know, we're sort of hippie, vegetarian, greeny bastards who are trying to undo proper quantitative science. You know, we were accused that we would be the end of quantitative herpetology, and we'd go back to studies about the frog in my backyard. And I think those who know me can know that that's actually not, I mean, we are vegetarian, probably a hippie, but you know, apart from that, you know, we're motivated by, initially I undertook this study because I was asked to clip some toes off some frogs when I was completing my PhD work, and I thought about it and I thought, no, I didn't want to do that. And then I thought, there's got to be an effect of that. Let's have a look. And that's what started the whole story. And I was young and naive then, but I was not prepared for the hostility, and I was not prepared for how resistant people would be to change. So it's been an interesting journey.
Yeah, yeah. And have any of you got advice for others who come across issues that where they have concerns? Either it's the appearance of a Western blot, or a flow cytometry blots, or statistics that look too good to be true. What can you do? How, you know, should you raise a concern publicly, and if so, what's the best way to go about it? Is it by using Twitter, or are there better ways, or is there no good way to do this?
I don't think Twitter is necessarily a good way. I would suggest that if one suspects fraud, and probably in none of these toe clipping studies is there actual deliberate fraud. I think it's just poor understanding of the scientific process and statistics combined with a bit of bias to want to see a particular outcome. So it's a bit of a different situation to the others. But I would say if you're in, I would suggest that people pursue, just be curious and look and keep looking and until they're satisfied, but also be prepared for opposition.
I'd just like to put a shout out to the website PubPeer. So PubPeer is a site where anybody can post comments on any published paper, and the comments can be anonymous, and it's quite robust anonymity. And comments pasted on any paper on PubPeer, there's an alert sent to the authors of the paper, but the postings, you judge the postings based on the evidence that's presented in the posting. So if anybody puts up something irrelevant or spurious, then the readers of PubPeer are left to make their own judgments based on the evidence that's actually presented there. So I urge everybody to look at PubPeer and have a look to see whether there are comments on some of these papers on ivermectin or on the effects of acidification on fish, because often you'll see the comments in PubPeer well before you'll see them elsewhere. But it is a good venue where people can report concerns without having to worry about retribution.
I'll just add to Kirsten's comment before that if you do suspect misconduct or something has gone on, don't go it alone. Reach out to your collaborators, get them to verify what you're seeing, because it's a long process going through this, and it can be very draining, and to have a good group of close colleagues to share the load with is really important.
And it's also particularly difficult if the people you have concerns about are from the same institution that you're in. In Australia, every institution that receives funding from the NHMRC or ARC must have some advisors on research integrity. So a good first step is to talk to them and get advice about what you can do, what you shouldn't do, what the potential risks are, and what your responsibilities are, and how you can go about raising concerns and minimise the chances of retribution.
I will say, just to add, I personally quite like Twitter and PubPeer. I use both. But I think that there's definitely a big difference between disagreements where there's some scientific rationale for the disagreements, and whether that be because people are doing bad statistics and you want to point that out, or because their studies aren't replicating, and people who may have completely fabricated results. The challenge, I think, is that journals and institutions generally, as I think everyone here has recognized, are terrible at revisiting their own published work. You have journals where they have published results that are impossible simply in the manuscript. I recently raised an objection in Nature Scientific Reports about a publication where the T and Z statistics are not consistent with the p-values in any of their tables. They have published the wrong T and Z statistics or the wrong p-values. I think both, actually. I think they've done both of those things. Nature and Scientific Reports has told me that it's a long and torturous process before they'll do anything. And that paper has been cited, I think, at least 20 times this year. So the problem is that if there are mistakes, obvious mathematical or statistical errors in a paper, the process is interminable, and raising issues publicly may be a more useful way to deal with the process, because nothing gets corrected until there is public outcry, even if it is obviously wrong. That being said, unless you've got very honest authors, and I've met a very honest author, he had a table where he'd miscalculated the population attributable fraction. And when I notified him of this error through PubBear, he immediately requested the journal delete the table. This is great,
yeah.
But it's very rare.
There's the lack of reproducibility in science is partly due to poor practices, and this is what more or less what Timothy said, and some of it's due to deliberate dishonesty. And there's an overlap, and there's a spectrum in both. One of the times I got interested in this issue was from reading one edition of Nature published in 2004. And in that one edition of Nature, there were 10 papers that had figures with error bars, but only 3 of those papers anywhere in the paper said what the error bars were. And one, it was standard deviations, one was standard error with mean, one, it was confidence intervals. But 7 out of 10 papers published in Nature, nowhere in the paper said what the error bars were. Now, I don't think this is an indication of dishonesty, because nobody would deliberately fake their data and then not say what the error bars are. You'd also fake the nature of the error bars. But it raises issues of how did those papers go through peer review? How come, and they're all multi-author papers, how come none of the authors read the papers carefully enough to realize that the error bars weren't named? And how did the peer reviewers judge the papers and the data in the papers and accept them for publication in Nature, given that they couldn't understand the data that were presented? And the same is true for the editors. So I concluded that 7 out of 10 papers appearing in Nature haven't been carefully read by the authors or the peer reviewers or the editors. But once again, this isn't a problem to do with misconduct. This is a problem due, related to the peer review process and poor scientific practices.
Yeah, I think the peer review process and editors generally are not good at catching numeric errors. I would say probably if you go through papers, aside from the papers published by pharmaceutical companies, because they pay someone a lot of money to check every single number in the paper before it's published, and they very rarely contain numeric errors, but the vast majority of papers you will see have at least one mistake. And the most common mistake that I've found is most papers have a percentage that's wrong. They put in a percentage, and they put in the number, and then they put the brackets percentage, and the percentage doesn't match the number. It happens all the time. It's a simple error to make, very easy to do. One string of code that you've got wrong, most people do it.
Well, I'd just like to thank the speakers once again for wonderful talks, and I'll hand over now to Fallon, who's going to organise the breakout room. So is that right, Fallon? Are you happy to do that?
I can. You just have to give me a minute.
Okay. Yeah. So once again, I've met Kirsten before, and I've certainly heard of both Gideon and Timothy. But you've done such fantastic jobs standing up for integrity in science that I take my hat off to you all.
Thank you very much.
Thanks, David.
Yeah. So all of the comments that are coming through are very positive.
You should just be able to pick the rooms. And speakers, I have moved you into your rooms.
All right. Well, I'll sign off then. Thank you.
Sure, David. Thanks for chairing.
It's a real pleasure. Thank you for organising, and thanks also to Fiona for the invitation.
I think Fiona's still here. But yes, I think it was a really, really interesting session. Hi, Matt. Hi, Jorge. We're in breakout rooms now. If you wanted to pick the speaker that you want to have a chat to,